In the previous lecture, we saw what a hard problem was. In this lecture, we're going to look at the main technique to show that a problem is hard. This technique comes from a reduction, but in this case, we use the reduction in a different way. Here, we have a problem A, and we know that problem A is already hard. For example, problem A could be the 3-sat problem. Then we reduce problem A to problem B. Remember, a reduction is some algorithm that's going to use an algorithm for problem B as a subroutine. Given this reduction, we know that if problem A is hard, then problem B must be hard, provided that our reduction is polynomial in time. And this is because if we had a polynomial time algorithm for problem B, this algorithm, along with the reduction, would create a polynomial time algorithm for problem A. But we know that because problem A is hard, there is no polynomial time algorithm. Therefore, there is no polynomial time algorithm for problem B, provided this reduction exists. That's the general idea behind reductions. To see it in action, we'll take an example. Usually, when we're talking about reductions, we're going to start with the 3-sat problem. 3-sat is going to take the place of problem A, the problem we'd like to reduce something to. The problem we're going to show that it's hard is the Klique problem. We just saw what the 3-sat problem is, but let's recall what the Klique problem is. In the Klique problem, we're given a graph, and in this case, we're looking at the decision problem of the Klique problem, so we're given some target. Our target will be k. Our objective is to deliver an output. In this case, our output is a yes or no answer. We output the answer yes if there's a clique in the graph of size at least k, and we output no otherwise. Remember that a clique is a complete graph. It's one where every possible edge that could exist does exist. Now we're going to reduce the 3-sat problem to the clique problem. To do this, we're going to have to map the input of the 3-sat problem to an input of the Klique problem. Remember, the input of the Klique problem is a graph, so from the 3-sat problem, we'll have to create a graph. This graph is created by creating a node for every literal in the 3-sat problem. So, for example, the literal x1 is going to be associated with some node in our graph. But we're going to have more than that. In fact, for every literal inside of every clause, we're going to create a node. So looking at the first clause, we're going to have a node for x1, a node for x2, and a node for x3. Looking at the second clause, we're going to have a node for x1, a node for bar x2, and a node for bar x3, and so on through all the clauses. In this case, we have just 3 clauses so that our graph is a little bit manageable. In addition to these nodes, we're also going to have to introduce edges, and we're going to introduce an edge between every clause that isn't a negation of itself. So, for example, there's an edge between the x1 from the first clause and the x1 of the second clause. There's actually an edge from the x1 of the first clause to every other node in this graph except for x1 bar. We don't connect any clause with its negation. We do this for every node and every clause. This is a transformation of the input. We've transformed the input of the 3-sat problem into the input of the Klique problem. Now we have to transform the output. Given an answer to the Klique problem, we have to transform that to an answer to the 3-sat problem. In this case, the transformation is straightforward. If we can find a clique whose size is at least the number of clauses, then we answer yes to the 3-sat problem. To see why this is true, we sort of think about it in reverse. In this case, we have a 3-sat problem, and we can satisfy all the clauses by setting x1 equal to true and x2 equal to true, or false, so that x2 bar is equal to true. If we do this, then we can verify that all 3 clauses are satisfied. In our graph, now, we can say that x1 is equal to true, and therefore we're going to connect all the true clauses together. That is, x1 is going to be connected to x2 bar, which is connected to x2 bar, which is connected to x1, making this triangle of blue. This triangle forms a clique of size 3. And we can see that this clique of size 3 has one node in every set of nodes corresponding to each clause. In some way, this clique and all the nodes in this clique are going to correspond to all the things that are going to get the value true. In this case, x1 is going to get the value true, and x2 bar is going to get the value true. So cliques in the graph correspond to valid assignments in the 3-sat problem. Now we can be more formal about our reduction. To transform the input, we're going to introduce a node for every literal in every clause, and we take the union of them to form our set of nodes. To make the set of edges, we make an edge between any pair of nodes so where the two nodes are in different clauses, that is, they come from different clauses, and U is not the negation of V. Finally, we have to set a target, and our target clique size is going to be the number of clauses. We're looking for a clique of size K or larger. Our output transformation is rather simple. If we can find a clique of size greater than or equal to K, then we output yes, meaning that the 3-set clauses can be satisfied. If we find a clique that is not of size K, then we output the answer no. We can convince ourselves by looking at the graph a few pages ago that this transformation is actually going to be correct. If we're looking for the actual assignment, we take all of the nodes that are involved in the clique found by our algorithm and set each literal associated with the clique to true. We should verify to ourselves separately that if we assign the nodes in this way, that this actually creates a valid assignment. Now that we've seen a reduction, let's focus on the important points about it. The first thing we have to do is identify the problems A and B. Problem A is going to be a hard problem. Problem B is going to be the problem of interest, the one that we'd like to show is hard. First, we have to transform the input of our hard problem, problem A, into the input of problem B. This transformation has to take polynomial time. Although we didn't mention it, in the case of our 3-sat reduced to clique problem, the reduction is polynomial time. This is easy to verify. Then, after we've transformed the input, we have to transform the output. In this case, we have to show that a yes for the decision problem B transforms to a yes for the decision problem A. Conversely, a no for the decision problem B has to transform to a no in the decision problem A. Here we're implicitly assuming that all of the problems we're talking about are decision problems, and in general, when we deal with reductions, we're going to deal with only decision problems. Some general guidelines for actually creating reductions. The input transformations are usually the hard part. Usually we have to think quite deeply about these. And we shouldn't get too caught up in targets. The decision problems all have targets, but the targets might map to different things in the different problems. Finally, we have to be sure that we actually map yes instances to yes and no instances to no. We should verify this by proving it to ourselves every time we do a reduction.